Hello and welcome to our lecture. Today we're going to be talking about panoramic imaging, a look into history, exploration, and future of the technology. I am Andrew Gruber.
Daniel Abelseth.
I'm Kevin Liu.
And I'm Wendy Yu.
And we are Dill Pixel.
So this is what we're going to be covering today. I'll start by giving a brief introduction and talk a little bit about the history of panoramic imaging. Then I will talk about the key design parameters for panoramic imaging systems. Then Dan will cover the bundle adjustment, and then Andrew will cover the techniques and stitching methods used in panoramic imaging. Then finally, Wendy will finish out the presentation by talking about the applications of panoramic imaging and its relevance to engineering, as well as the future of panoramic imaging. So basically, panoramic imaging refers to the technique of capturing a wide-angle view or a 360-degree perspective of a scene. It's a method that allows photographers or imaging systems to create a seamless, extended view that covers a much wider field of vision than a standard photograph. Instead of capturing a limited frame, panoramic imaging stitches together multiple images, which Andrew will talk about in more detail later, or uses specialized equipment to create a single continuous image. The concept of panoramic imaging dates back centuries, and as early as 20 AD in Pompeii. During that time, panoramic murals were used to capture scenes and were later evolved into 360-degree panoramas by Robert Baker. Robert Baker would use up entire buildings to house his 360-degree panoramas. Then Frederick von Martin developed a panoramic daguerreotype using a specialized camera he designed so that people didn't have to rely on painting techniques. Daguerreotypes were created using a polished, silver-coated copper plate, and the plate was treated with a light-sensitive chemical, exposed in a camera, and then developed using mercury vapor to reveal the image. And in the 19th century, Joseph Puchberger submitted one of the earliest patents for a panoramic camera in 1843, which featured a hand-cranked mechanism and a 150-degree field of view. Then, Frederick von Martin created his own panoramic camera in 1844, which utilized curved plates and set gears. Then in the 20th century, advancement in film and camera technology revolutionized panoramic photography. Cameras like the Circuit and other rotating panoramic cameras enabled the capture of wide-angle views on film, paving the way for high-resolution panoramic images. And later, in the digital age, brought about software-based stitching techniques, enhancing the ease and precision of creating panoramic images. These advancements laid the groundwork for the more sophisticated panoramic imaging we have today. So now I'll go over the key parameters for designing panoramic imaging systems. I'm going to start with a brief description of the parameters, and then I will talk about each one in greater detail later. The field of view is the angle determining an optical system's range. The wavelength is the spatial period of a periodic wave. The F number is the ratio of the focal length in the image space of an optical system to its entrance pupil diameter. And the focal length is the distance from the primary point of the optical system to the focal point. The resolution is the ability of a measurement or display system to resolve the details. The imaging quality is pretty self-explanatory. It's just the imaging quality of the system. And the volume refers to how compact the system is and the compactness ratio of the panoramic system. The field of view, or FOV for short, determines the ability of the camera to observe the range of the surrounding scene. There are 4 ways to express FOV. You can express it in an angle, object height, coaxial image height, or actual image height. Panoramic imaging instruments usually take the angle as the evaluation standard of the FOV, and in practical applications, full angle FOV is generally used. And when designing a panoramic optical system, the expression of 360 degrees times half the FOV is usually used to represent a panoramic system with a blind area. The figure on the right here shows the different types of angles for FOV and how it affects the ability of the camera to observe a scene. So as you can see, The smaller the FOV, the longer the focal length, and the less of the scene the camera can capture. So in physics, wavelength is defined as the spatial period of a periodic wave. And electromagnetic radiation can be classified by wavelength as radio waves, microwaves, infrared, the visible spectrum, ultraviolet, X-rays, and then gamma rays. The spectral range in which the human eye can perceive the world is called visible light, which usually have wavelengths in the range of 400 to 700 nanometers. Light wavelengths longer than the visible spectrum are called infrared, and light wavelengths shorter than the visible spectrum are called ultraviolet. Ultraviolet wavelengths range from 10 nanometers to 400 nanometers and are shorter than visible light, but longer than X-rays. Typically, infrared, or IR for short, wavelengths range from 700 nanometers to 1 millimeter. Obviously, the most common range for panoramic imaging systems is visible light, but in order to expand human perception of the surrounding environment, UV and infrared panoramic imaging systems have emerged to enable a wider spectrum of environmental perception beyond the human visible spectrum wavelengths. Now, the F number of an optical system is the ratio of its focal length to the diameter of its entrance pupil. Basically, it's just a ratio describing how much light an optical system can gather. And smaller F numbers means more light entering, which is good for low light conditions and fast-moving objects. And low F numbers create sharper focus on the object, but it blurs the background more. However, high F numbers give clear images across various distances with less light. Also, smaller F numbers have wider applications, but are harder to design, while larger F number systems are easier to design, but might have lower image quality. And for panoramic systems, a smaller F number is usually used to ensure good imaging quality and a larger amount of light. The figure on the bottom here shows how the F number works and its effects on the image. As you can see, the smaller the F number, the bigger the aperture gets. So f1.4 lets in a lot of light, but blurs the background. And f8 lets in very little light, but creates sharper, more clearer image. The focal length is a distance from the center of an optical system to where the image focuses. Panoramic imaging relies on different projection models like the equidistant projection model, which is often used for wide-view optical systems. In this model, this equation shown here shows the image height depends on the focal length and half of the FOV. Y is the image height, and F is the focal length, and theta is half of the FOV. When the field of view remains constant in a panoramic system, a larger focal length means a taller image, but this also increases the system size, and a larger image height often leads to a need for higher resolution sensors maintaining the same sensor pixel size. Resolution refers to how well a system can capture details. In a panoramic system, resolution is about the total number of pixels, like 4,216 by 3,128 for a 13 megapixel sensor. The pixel and sensor's resolution determines its optical format, and for an optical system, the resolution is linked to the wavelength of the light and the size of the aperture. Smaller wavelengths and larger apertures generally mean higher optical resolution, especially when correcting for system errors. The figure shown here is a comparison between a high-resolution image on the left and a low-resolution image on the right. So in panoramic systems, image quality isn't judged by just one thing. The main factor affecting it is aberration, like spherical aberration, coma, and others. And these can distort images. And in panoramic imaging design, designers use things like the spot diagram and the modulation transfer function to check image quality. Spot diagrams are graphs that show where rays from a point object will fall on the image surface. So they have to fall close together if the lens is to form a good image. And the figure on the bottom here shows what spot diagrams look like for different types of aberrations. The spot diagram At the top is what you would want your spot diagram to look like. And a model transfer function measures the ability of an imaging system to reproduce the context of an object. Basically, it quantifies how well the system can transfer contracts from the object to the image. The volume is just a ratio comparing the system size to the sensor's imaging circle. Basically, it just measures how compact it is. The ratio helps judge how efficiently the system uses space. The equation shown here is how the compact ratio is calculated, where R compact is the ratio of compactness, D sensor is the maximum diameter of the imaging circle on the sensor, and D panoramic is the maximum lateral diameter of the panoramic optical system. Smaller and lighter panoramic optical systems work better in tight spaces or where weight is a concern. Nowadays, researchers focus on making these systems smaller, with better performance and resolution to meet the standards of panoramic photography in compact form. And this involves careful consideration of various parameters during the design phase. Now I'll hand it over to Dan, who will go over the bundle adjustment of panoramic imaging systems.
Hello all, I'm Daniel, and the component of this lecture that I will be presenting is some bundle adjustment methodology in the context of panoramic imaging. This section of the lecture mostly boils down just into one possible approach towards performing a bundle adjustment on panoramic images, specifically a combined approach, which makes use of panoramic and central perspective images. Most of the research conducted for this component was performed by doctors Danilo Schneider and Hans-Gerd Maass out of the Dresden University of Technology in 2005. As I'm sure you're all well aware of by now, the bundle adjustment is a tool that combines individual elements such as geodetic and photogrammetric triangulation, along with space resection and camera calibration to accomplish 3D object reconstruction from 2D imagery. Of course, it is a crucial step in the completion of ENGO531 practical exercises. Just to give a bit of an overview here, we're going to be going over the model and coordinate system used for the adjustment, some of the parameters and panoramic specific parameters, image acquisition methodology, and the result of the adjustment. So the primary close range panoramic sensor used in this particular study was the KST iScan M3, cutting edge technology for 2005. The camera used a lens adapter to accommodate 4 potential high performance Rodenstock lenses, focal lengths 35 millimeters, 45 millimeters, 60 and 100. You can see in the figure there. The camera used in the acquisition of central perspective images was the Nikon D100 digital camera. While the panoramic camera is digital, does not comply with the geometric model of run-of-the-mill central perspective image captured with a more traditional digital camera. As a result, the geometric model had to be developed for the purpose of this adjustment. So the geometric model used for this adjustment had to be developed with a primary focus on modeling deviations from a more basic model using additional parameters. The exterior and interior orientation parameters were then estimated by implementing the model in spatial resection and intersection procedures using a calibration room. Goes without saying that where the model is concerned, the coordinate system is not too far behind. In this instance, 360-degree 3D cylindrical coordinate system is used to achieve the camera, or describe the camera geometry. My apologies. Concerning the attached figure, the z-axis represents the axis of rotation, while the x-axis defines the direction of the first column of an image using a traditional pixel coordinate system. These are described by M and N in the figure there. In order to describe the cylindrical nature of the object point mapping, a number of transformation equations were developed. The transformation between object coordinates and Cartesian coordinates is defined by equation 1, where R is the rotation matrix. The transformation from Cartesian camera coordinates to the cylindrical coordinates is defined by equation 2 there, where R is the radial distance between the rotation axis and object point. Image points within the cylindrical coordinate system is similarly defined in equation 3, where R is the radius of the cylinder, or principal distance in an ideal scenario, and Z is the image point height above the XY plane. The rotation angle remains the same for its respective object point and image. Finally, to transform between the cylindrical coordinate system and pixel coordinate system, the expressions are defined in equation 4 there, where n is the number of pixel rows, eta naught is the y component of the principal point, xi naught is the x component of the principal point, with AV and AH defining the vertical pixel pitch and horizontal resolution, respectively. After transforming from equation 1 to equation 4, we're left with the final object to image transformation equations defined in the top right there, where R is just an element within the rotation matrix. So the adjustment parameters are displayed in the attached table. The inclusion of additional parameters beyond the exterior and interior orientation parameters improved the standard deviation by an order of magnitude. This was verified through spatial resection and worked out to be 0.24 pixels. As for image space and for object space, it ranges from 0.1 millimeters to 0.5 millimeters, depending on the distance from the camera position. Nominal parameter and adjusted parameter values were not presented in this study. The attached table there provides insight into the impact, the number and type of disposition on the overall model fit, indicating that 6 horizontal positions with 1 vertical leads to generally the tightest model fit. This pertains mostly to the initial calibration and not the adjustment itself. Looking at equation 5 there, the result of the model development yielded the collinearity equations, adapted for panoramic images. The aforementioned transformation equations are also employed in order to transform values into global system. The last terms, dx prime and dy prime, at the end there describe additional parameters that are calibrated during the bundle adjustment process. So for image acquisition, 360-degree test field was established in the approximately 45 by 45 meter courtyard within Dresden University campus. Approximately 100 retro-reflective targets were distributed throughout the field, placed up to 20 meters high. The panoramic camera is fixed to a high-precision turntable, utilizes a PC-operated DC motor. The camera rotation speed, such that no gaps or overlaps present after a 360-degree rotation is completed. 4 360-degree panoramic images were required, along with 4 central perspective images, with the camera positions roughly represented by the attached figure there. The bundle adjustment was performed twice, once using the 4 panoramic images alone, once with an additional central perspective image. The model used for the combined central perspective image is described by the collinearity equations outlined here. So this is a combined adjustment and also includes the aforementioned derived panoramic collinearity equations. The figure attached there describes a theoretical example, the design matrix that would potentially be used to adjust 9 object points measured with 3 panoramic images and 2 central perspective images. For the result of the bundle block adjustment, adjustment performed in this instance, it demonstrates pretty strong precision and a tight model fit with the 4 panorama images alone. From the attached table, you can see that the standard deviation effectively remains the same after adding the additional central perspective image. However, on inspecting the RMS Z value, it appears that the additional image proves the overall model fit, indicating that the additional observations serve to stabilize the network geometry observed throughout the process. The conclusion of the study indicated that further testing would be necessary in order to determine if the method explored is more effective than a conventional approach. The intention of this component of the lecture was to present bundle adjustment in the context of panoramic imagery. This case study was chosen specifically due to its combined nature, which includes elements of our chosen topic, along with elements we have more familiarity with, such as bundle adjustments using central perspective images. And with that, I will hand it over to Andrew with image stitching and ortho rectification.
Thank you, Dan. That was lovely. My name is Andrew, and I'm going to talk about panoramic techniques and methods. Basically, Dan covered the bundle adjustment, getting your refined parameters and finding your camera calibration, but now you have to bring all those images together and stitch them into one to make one seamless and continuous panoramic image. First thing we're going to talk about is camera stitching methods, or field of view stitching. And what field of view stitching is, it's the process of using multiple fields of view to capture imagery, which is then stitched together to create a wide angle panoramic image. And the first method in acquiring these photos is single camera. As the name suggests, it's a single camera, generally on a mount or on a rotating mechanical stage, which rotates around a central point to capture imagery in a set field of view, which is generally less than 360 degrees for this method and more suited to a static environment. Since the camera has to rotate as it scans, it's not good for capturing dynamic imagery, say if you were tracking someone's eyes or tracking movement. And then another method, which is a little more complicated, a little more expensive, is multiple camera field of view stitching. And what this is, as the name suggests, is multiple calibrated cameras, which shoot simultaneously, generally to capture a full 360-degree view. But this method comes with its fair share of challenges and expenses. To create a nice even mosaic, the cameras have to all be set up with the same parameter settings and capture angles. So if those are different or there's any deviation, that's going to create problems in the stitching process. This method is far more capable of capturing dynamic scenes since nothing has to rotate and the cameras are all operating continuously. Obviously, this is not all of the methods for capturing panoramic images. There's different lenses you can use to capture wider fields of view. But for now, we're going to focus on field of view stitching and then stitching these images together. So once you've captured your images, the process then becomes to bring them all together, make it one continuous, seamless image like you would see on your iPhone. So this process generally involves acquisition first, obviously, which you would do with these single or multiple cameras. And then you would go into pre-processing and image registration. And finally, you would get into the blending and composition of the images. The boring bit, which is pre-processing, is a really important step. It helps simplify the alignment later on, and it's really important to the quality of your final alignment, so how good your pre-processing is. And what this is taking the individual images and identifying image interferences, so blur, noise, scaling, rotation, warping, segmentation, or if you have two images of different brightnesses, say there's a shadow, as you were panning, you'd want to match those beforehand, and that's going to help you simplify the process of merging these images together. Now for the fun bit, and that is image recognition. And this really ties into sort of what we did in 531 Lab 5 for Lab 3, Lab 4. And it's essentially just the process of identifying distinct features and corners between images and then matching them. This is generally done through an algorithm, an automated algorithm, which will seek out these points and match them. But I should note that this is not the only method of matching images. There's another method called the direct method, which is taking pixel intensities and comparing those. Each pixel intensity of the image is compared with another, and then you match it that way. But this method, you can't change scale or rotation, and it limits your convergence range. So for today, we're going to focus on feature detection. It's far more relatable for us. And what feature detection algorithms do, they take descriptor data to compare matching points on the images. It's basically just the process of extracting the best features in each image and matching them. Angles are also very useful points that they can take because you can use them to detect perspective change. And this process is done with complex matching algorithms, which I won't describe here because it's a little above the head level. So now we've aligned our images, we've identified key features, and we can match them together. But we still have the problem of the seam look, which is essentially, there's going to be seams in between the images, and we want a continuous panoramic image. So what we're going to get into now is image blending and the Gaussian pyramid technique. And essentially, of what the Gaussian pyramid is, it's just a way to combine images of different resolutions and frequencies. They're merged and filtered from the center of the image to give it a continuous look. And I won't get into exactly how a Gaussian pyramid works. It's a fairly complex process, but it's called a Gaussian pyramid because when you're resolving it, you keep them in a stack of highest resolution image at the bottom and lowest resolution image at the top. So that creates sort of that pyramid shape. And we have an example of this here with an apple and an orange. You can see using the Gaussian pyramid technique sort of gives it that continuous look. It's not perfect, obviously. We have two different images. But say we had a continuous landscape with overlap between images and they're perfectly aligned, that would give us that continuous panoramic look with no seams. And we're happy. Here we got a quick example of proper and poor alignment and image stitching. On the left, you got that nice continuous panoramic image. And on the right, there was a problem in your alignment or in your blending process. So you sort of get that seam there, you see. It's not continuous and it's not what we want. It's ugly. And now sort of a quick tangent, but I want to talk about another method, which is fisheye panoramic systems. This is away from field of view stitching, but I want to cover it because it's probably something you've seen on the internet. You see it in a lot of extreme sports videos and stuff, or you also might see it at your local gas station if you're on the security camera. A lot of the time you're on a fisheye panoramic lens. And if you took ENGO531, you've probably seen something like this. You know the principles of how a fisheye lens works. It has a short focal length and a convex shape, and it causes incoming light rays to bend more towards the edges. Refraction, you know about this, and it allows the lens to capture light from a wider field of view than would be possible with your standard lens, as you can see on the bottom left there. And this is useful for dynamic scenes like a security camera in your gas station, but it's not super practical for direct engineering purposes because it causes a lot of distortion on the sides, and you can see that on the bottom right. And with that high distortion level, you can't make direct, accurate measurements. So it's just not super useful. Now let's zoom out a little bit. Obviously, when you think of panoramic imaging, you think of capturing a sunset or that beautiful view at the end of your hike. But the purposes of panoramic imaging extend far beyond this to a lot of engineering purposes for imagery and satellites and mapping. I won't delve too much into this because Wendy will discuss it in the application section, but I want to get into a proposed technique for orthorectifying satellite radar panoramic images and how you would do that if you had a DEM. Now, you probably all know a little something about orthorectification, so this might be a review for you, it might not. But what orthorectification is, essentially, is just the process of removing distortion from our images to create that ortho image. Without it, we wouldn't have a constant scale or accurate distances, and these are going to be important for engineering purposes. For the purposes of this lecture, I'm not going to cover actually how you acquire these images. I want to focus on orthorectification for the panoramic images. So let's assume we have our necessary inputs, which is a set of panoramic images and an accurate digital elevation model of the area, or a DEM. Now, these panoramic images are acquired as slant range images. And essentially what that means is just an image where each target is located relative to the radar's position, which is our slant range D, as you can see on the figure on the right. And when we're looking to combine these, obviously our radar's moving. There's going to be line of sight changes for objects in the environment. So we're going to want to correct each one individually. Bit of a process. So first things first, we got to express our raw pixel coordinates in the same system as our DEM. So we have our north-oriented panoramic images, which are initially centered around our radar's position. And the sensor will obviously be equipped with a GPS, so we can get our heading parameter, and we're oriented with a gyrometer, which means we have our radar's position XR, YR, and ZR. And we also have the image's resolution. So in combining those, we can express our raw pixel coordinates in the same coordinates as our DEM. Now comes the issue of determining this pesky delta Z value. And what delta Z is the elevation difference between the scanned environment and our radar. It would be nice if we could measure these directly from the DEM or from similar triangles. But often what happens is this slant range, D, is what's called overestimated, which just means our total distance, our measured distance is greater than our true distance. That's overestimating. So we can't just measure it directly or solve for it directly with triangles like would be easy in figure on the bottom there. So, and obviously the goal of all this is to get our planimetric distance, which will give us our true geometry and remove our distortion from our images. But this process isn't simple. We can't just measure them directly. So we have to break apart some equations, and I'll get into how you solve it. Now, those parameters might have been a little confusing on that last slide. I'm hoping we can offer some clarity here on what everything means. So from the figure on the right, you can see that our planimetric distance P on the bottom down there is equivalent to square of our slant distance squared. We can't measure directly. We got to form some relationships. So from the figure, you can see our planimetric distance over our slant distance is equivalent to our change in elevation, our delta Z, over the elevation of our DEM minus the elevation of our radar, ZR. But same thing, sort of the same issue here. We can't directly solve for that change in elevation. So we form a relationship with respect to our planimetric distance. And solving for this, plugging in our values, we can get an equation that allows us to solve for a planimetric distance without getting that change in Z. We can use our elevation, our DEM, elevation, our radar, and our slant distances. And with that nice planimetric distance, we can remove distortion, get an ortho image from our satellite panoramic images. Generally, you would want to ground truth this after, but I'm not going to cover that. It's not really relevant to us. Obviously, sort of a condensed summary of orthorectification. We're on a time crunch here, but I want to cover it as it adds some context into when Wendy talks about all the applications of panoramic imaging, and she gets into how it's used in engineering and geomatic purposes. But first, we have this figure for you, which is a raw radar scan compared with an orthorectified radar scan. Top left is raw, top right orthorectified. You're probably thinking to yourself, that's the same image twice. Fair thought, but you can see down here on the bottom, that's some context where the blue is removed echoes and the red is sort of added echoes. So sort of how it has shifted once we get those correct geometry and once we finish that process. Now I'm going to pass it over to Wendy, and she's going to talk about the application of geomatic and why this all matters and how we're going to use this.
All right. Thank you, Andrew. As mentioned, I am Wendy, and I will be presenting on the applications of panoramic imagery. How is panoramic imaging applied in the field? How does it tie into geomatics engineering? Panoramic imaging holds significant relevance to the field of geomatics engineering. As geomatics engineering involves the collection, analysis, and interpretation of spatial data, panoramic imaging can play a crucial role aiding in the stereo capture of scenes up to 360 degrees and enhancing the capabilities of existing geospatial data acquisition methods. This will be further elaborated upon in the following example. The wide field of view offered by panoramic imaging facilitates efficient surveying, mapping, and overall acquisition of data. It can allow for a quick but comprehensive visualization of geomatics applications such as urban planning, environmental monitoring, and infrastructure development. Panoramic imagery has been known to be integrated with other forms of data collection. For example, it is a large aspect of laser scanning and building point clouds. By stitching together data from both multi-view aerial images collected from unmanned aerial vehicles and ground panoramic images, researchers John, Curl, and Rao were able to produce comprehensive and rapid results for investigating post-disaster building damage. For this study, the ground panoramic images were collected with a Ladybug 5 spherical camera. The Ladybug 5 uses 6 wide-angle lenses that capture 6 original images, 6 undistorted images, and most importantly, 1 stitched panoramic image. For this system, the collected ground panoramic images are non-ideal panoramic images, as the spatial resolution is much higher than the spatial offsets. Although using the longest spherical radius produced the best results compared to other radii, the results produced were still unsatisfactory for the purpose of accurate 3D imagery. Thus, what the data from the ground panoramic imaging lacked, the data from the unmanned aerial vehicle supplied, and vice versa. The 3-dimensional point clouds generated from the integration of the two were notably more accurate. Where the aerial images were lacking in suitability for lower floor, dense areas, the ground panoramic images were able to compensate. In the figure on the right, it can be clearly noted that the point clouds from the combined multi-view aerial image scans and non-ideal panoramic images have a higher percentage of coverage or completeness, with less gaps in the data. So, moving on to more modern applications of panoramic imagery, the School of Automation and Electrical Engineering in Linyi University research panoramic image processing based on virtual reality technology. The rising interest in virtual reality has led to innovative uses of many technologies, panoramic imagery included. In virtual reality, the application of panoramic imaging can produce a higher sense of immersion. However, the application in VR is much more difficult when compared to a traditional 2-dimensional panoramic image. The requirement of repeatedly mapping the image to a sphere and then projecting it to a visual plane for the viewer can result in distortion or loss of quality from the original image. This technology was still rather limited in 2019, but was on a fast track of continued development and research, as it is comparatively cost-effective, but was still able to produce convincing representations of environments. This use of panoramic imagery is not used only in virtual reality, but commonly used in other similar applications, such as walkthroughs of buildings. These walkthroughs have become increasingly common in relation to real estate. It allows for a 360 tour of a listing without actually needing to be physically present. So, this use of panoramic imagery is not only used in virtual reality, but also commonly used in other similar applications, such as walkthroughs of buildings. These walkthroughs have become increasingly common, especially in relation to real estate. It allows for a full 360-degree tour of a listing without needing to be physically present. Below is an example of such an image. This flat 2-dimensional image has distortion at the top and bottom, which will smooth out once it is wrapped into a 360-degree image, and this will produce the immersive effect. So, moving on to other applications, panoramic radiography or panoramic X-rays are a common practice in dentistry. It allows the dentist to capture the patient's mouth in a single image, including not only the teeth, but also the surrounding tissues. Out of the X-rays commonly performed for dentistry, panoramic X-rays have one of the lowest radiation doses and can be performed quickly due to its simplicity. It can visualize areas that are difficult to capture with other forms of radiographs. However, it does come with its own drawbacks, which will be further discussed later. The use of panoramic imaging has also been tested in the analysis of bloodstain patterns in crime scenes. A study was conducted on the viability of using panoramic imagery to record the scene and construct a digital panorama. This method would allow crime scene investigators to record impact patterns even without extensive training on bloodstain pattern analysis, and allows experts to digitally and remotely analyze a single image as opposed to several separate images. Unlike previous methods, which would require multitudes of images taken at varying distances, using panoramic imagery would allow for the inclusion of close-ups of the splatter pattern while still retaining the context of the scene itself. The study concludes that it was possible to use panoramic images for effective and repeated offset determination of the area of origin for splatter patterns. As previously mentioned, panoramic X-rays are not without fault. The images are not as sharp compared to some other forms of X-ray imaging, as it is composed of the stitching of multiple images. This loss of clarity and fine details makes it less ideal in detecting smaller complications, and objects outside of the focal trough can appear distorted or potentially not appear at all. Panoramic images can be obtained in two ways, either through a calibrated spherical camera, a fisheye lens, or by stitching images together. In systems that use multiple lenses, the latter is employed. However, errors can occur when the images are stitched. These errors occur when the spatial resolution is greater than the spatial offset and require the inclusion of a spherical radius to reduce the errors. The stitching together of images can also potentially lead to a loss of clarity in the compound image. As mentioned before, panoramic imaging on its own can have unsatisfactory results when it comes to modeling 3D imagery accurately. In the case of virtual reality integration, a loss of image quality and distortion can occur due to the repeated mapping and projection necessary to produce the immersive effect. The goal of this lecture was to provide insight into the theory and methodology associated with panoramic imaging, as well as explore applications of the technology. To summarize, panoramic imaging is the technique of capturing a wide angle or full 360-degree perspective of the scene and stitching together multiple images to create one continuous scene. Innovations in the 20th century sped up the advancements of panoramic imagery, leading to higher resolution images. Single camera and multiple camera stitching methods exist, each better suited for their own purposes. Static images for the former and dynamic imagery for the latter. There have been and will continue to be many applications for panoramic imaging, a few examples of which include the collection of spatial information via panoramic laser scanning, generation of realistically convincing environments both in and out of virtual reality, and assistance in forensic investigations. The technology has steadily evolved since the early inception of panoramic photos and will only continue to grow from here. And that is the conclusion of our presentation. Thank you very much for watching, listening, and have a great day.